Hi everyone, my name is Prashant Srivastav. I'm a PhD candidate at Purdue University, and today I'll be presenting to you Gramatron, a framework for uncovering deep bugs in language interpreters using grammar automatons. This work was done between myself and my advisor, Professor Mathis Pyle at EPFL. Interpreted languages such as PHP, Ruby, and JavaScript form the backbone of our web ecosystem. As such, securing the interpreters for these languages is an important task. Language interpreters generally take in structured input, and the structure itself is defined in the form of a context-free grammar. To give you some brief background, context-free grammar represents the derivation structure of inputs. This derivation structure itself is called parse tree. And here we have a simple example of a sample code snippet and its corresponding derivation structure from a sample grammar. Here the leaf nodes are known as terminals, and the non-leaf nodes are known as non-terminals. So fuzzing itself is a very effective software testing methodology, and here we present a simple fuzzing workflow where the mutation module takes in a set of seed inputs. It then generates mutants from the seed inputs, referred to as a fuzz input, tests it on the fuzz targets, and collects coverage feedback to guide its mutations further. When it comes to fuzzing language interpreters, especially if we want to fuzz past the parsing stage, we need to generate syntactically valid inputs. To that end, there has been extensive work done to figure out how to incorporate grammars into this fuzzing workflow, which is referred to as grammar-aware fuzzing. The methodology followed for grammar-aware fuzzing is as follows. Given an input and the knowledge of the grammar, the mutation module generates the corresponding parse tree for that input. It then performs mutations on top of this parse tree with the knowledge of the grammar, so that the mutated parse tree is still syntactically valid. And then it's a simple matter of just performing an in-order work of the parse tree to generate the actual concrete input, which can then be tested on the first target. For one observation is that for complex bug triggers require use a wide variety of grammar features. And we see two main drawbacks with the existing approach for grammar-aware fuzzing in the context of synthesizing these complex bug triggers. First is the problem of bias sampling, where a fuzzer, if it's sampling uniformly at random from existing grammars as is, it gets biased towards generating certain constructs more than the others. And this problem can be visualized with a simple example where we see that even though the call statement rule can generate twice as many unique inputs as red statement rule, it still has the same probability of being picked by a fuzzer for input generation. And this problem of bias sampling can be especially a hindrance when you're trying to synthesize complex bug triggers, because they require chaining multiple parts of the input state space. Then there is the problem of small-scale mutations, where existing mutation operators operate at the subtree level granularity, and they keep the prefix and the postfix of the tree intact while performing the mutation as visualized here. This can especially be a problem if the fuzzer gets stuck fuzzing parts of the grammar that are not relevant towards triggering the complex bug, and being stuck in local minimas of coverage. For the first problem bias sampling, we restructure the grammar itself to eliminate the sampling bias. And for the problem regarding small-scale mutations, we redesign the mutation operators to perform large-scale mutations instead. To perform the unbiased sampling coupled with these large-scale mutations in an efficient manner, we model the grammar as a finite state automaton, referred to as grammar automatons from here on out. So, and now I'll present to you the design of Gramatron, which is a coverage-guided grammar-aware fuzzer that uses grammar automatons. So the first step is the grammar preprocessing phase, where the context-free grammar is converted into its corresponding GNF form, which has a twofold advantage. It eliminates the sampling bias, and it enables the Gramatron to generate a more concise automaton. After which, Gramatron uses the technique of regular approximation to generate the grammar automaton itself. Once this automaton is generated, we move on to the fuzzing phase, where this automaton is passed on to the mutation module, which uses it to generate syntactically valid test inputs, which are tested on the first target, and then coverage feedback is collected to guide those aggressive mutation operators further. One key insight that we had is that fuzzers do not generate arbitrarily large inputs, and Gramatron uses this insight to generalize its grammar transformation to any arbitrary context-free grammar by limiting the complexity of language constructs. This is an acceptable trade-off since existing grammar-aware fuzzers already do that. For our evaluation, we compared against Nautilus, a state-of-the-art grammar-aware fuzzer that uses probabilistic sampling to generate larger inputs and also localized mutations, small-scale mutations on top of parse trees. First, we evaluated whether Gramatron performs unbiased sampling as compared to other approaches by using branch coverage as a proxy metric. We see that it's able to uncover up to 24.2% more coverage compared to other existing state-of-the-art approaches, showing that it is able to generate higher diversity inputs corresponding to richer semantics. Next, we evaluated whether Gramatron is efficient in terms of space and time by performing this unbiased sampling and these aggressive large-scale mutations. So, and we generated micro benchmarks to separately evaluate each of these aspects. So for our space micro benchmark, we calculated the size on disk for inputs represented as automaton walks and compared them to inputs represented as parse trees as done by Nautilus. And this is what is represented on the y-axis. On the x-axis, we have the size of the inputs in terms of the number of terminals that they contain and different intervals for the same, which is on the x-axis. So as you can see, Gramatron is able to, the input represented as automaton walks are 24% smaller. Then we evaluated whether Gramatron is faster at generating inputs from scratch from the grammar. And the time taken to generate these inputs from scratch is what is represented on the y-axis. As you can see, Gramatron is able to generate inputs 98% faster. And the main reason behind this is the fact that Gramatron does not need to keep track of the parse stack while it's performing this input generation. Even though Gramatron is performing these large-scale mutations, we see that it's still faster. We see that it's still 68% faster than Nautilus, which is performing these localized small-scale mutations. There's a twofold reason for that. First is the fact that our input generation is faster, and second is the fact that the redesigned mutation operators reduce the runtime complexity of certain mutative subtasks as well. Then we also evaluated the degree to which Gramatron performs these large-scale changes and the scale of them. And for that, we calculated the size of the mutant substring that is generated from these aggressive mutation operators, and which is what is like calculated on the y-axis. And we can see Gramatron is able generates mutations that are 6.4 times more large scale than the mutations that Nautilus generates with its localized mutation operators. This means that it has a lower chance of being stuck in local minimums of coverage. Then we evaluated whether the aggressive mutation operators used by Gramatron can help in uncovering complex paths faster. So for this evaluation, we collected a corpus of 10 ground truth bugs across 3 interpreters. We ran multiple 24-hour campaigns to find those bugs with the different tools. And for this experiment, we calculated the number of successful campaigns, which is whether the tool found the bug within the allocated time budget. And then we also calculated the median time to discovery across the multiple trials. So and we divide the discussion between simple bugs and complex bugs. So for 3 out of the 7 bugs, we see that Gramatron is able to outperform Nautilus. Then which is for PHP1, PHP2, and JS3. For JS4, we see that it's right behind Nautilus GH in terms of uncovering the ground truth bug. For the remaining 3, which is PHP3, PHP4, and MVP2, we see that Nautilus is able to outperform Gramatron. And the reason behind this is the fact that the localized small-scale mutation operators used by Nautilus are better at uncovering these simple bug triggers. However, for complex bugs, we see that Gramatron can find these complex bugs reliably and much more faster than Nautilus. And the reason is that the aggressive mutation operators used by Gramatron prevent it from being stuck in local minimize of coverage, and it performs a more global search through the input state space, allowing it to uncover these complex bug triggers faster. Finally, we evaluated the real-world efficacy of Gramatron, and for that we deployed a 10-day campaign for 3 popular and well-tested interpreters. Over the course of these 10 days, Gramatron was able to uncover 10 new vulnerabilities. To conclude, unbiased sampling coupled with aggressive mutations enable deeper testing. Grammar automatons make performing this deep testing efficient. And Gramatron is able to outperform existing state-of-the-art grammar-aware fuzzer, which is Nautilus. Finally, the code for Gramatron and the artifact to reproduce all our experiments is available at this link. Thank you.